think you were explaining how we met, and we sort of connected on the brain first from a systems perspective, and then really started to get along. So I'm really thrilled to be here and to share the opportunity. I'll talk a bit more about myself in a minute, but I'm going to do 4 things today, right? So one is to essentially try and get the message across, which I think you've already got, about why systems thinking, modeling, and simulation are so amazing. Competencies that help us change the world. What it is, how we can go about doing it, and then at the end of it, I sort of hopefully want to come away with a message that resonates with everyone, where you actually remember that you actually knew this anyway. We just forgot it while we were growing up and we started to do things differently. So, but before I start, I want to sort of tell you a bit of a story that really summarizes the context. So this is going back to the 1950s in the island of Borneo near Indonesia. There was a big outbreak of malaria. A lot of people were dying. Mosquitoes were killing them, and they were getting malaria and dying. And so they asked for help. And at that point, it was the World Health Organization, WHO, had just been started up. And so the World Health Organization came in and said, we know how to fix this. And so they came and they sprayed a chemical to kill the mosquitoes. The chemical was called DDT. Those of you who are my age or older will probably remember what DDT is, but it was a very bad chemical. It killed everything that it touched pretty much. But it fixed the problem. So people stopped dying, they got better. But then after a little while, something started to happen. So the first thing that started to happen was the roofs on the huts started to fall down. All over the villages, they started to lose their huts. Seems strange, but people built again. And then something worse happened. After a little while, there was an outbreak of typhus or the plague. Very bad sickness, right? And people die again. So they raised the hand up, called the WHO and said, we need help. This is pretty serious. WHO thought about this and said, okay, we just fixed something there. How come there's another problem? So this time they thought, we better go and check what's going on. So they sent people out to Borneo to check. And what they found was really interesting. What they found was that when they sprayed DDT, they killed the mosquitoes. Great, everyone was happy. But then what happened was that it also killed a type of caterpillar that used to prey on a bee that used to prey on a caterpillar. And when the bees died, the caterpillar population went up, and they started to eat the thatch on the roofs, and the roof started to fall. One of the reasons. The second thing that happened was the mosquitoes that died were eaten by lizards. So lots of lizards, they ate mosquitoes, geckos. Now they're very strong, so nothing happened to them. But cats used to eat the geckos, and the cats ate the gecko, and they got the DDT in their systems, and they couldn't survive, and the cat population died. When the cat population died, the rat population increased. And then with that came the plague. And so they thought about it now and said, we need to do something a bit more carefully this time, not a quick fix. So anyone know the story? How do you think they fixed the problem so that it was a good fix, not a quick fix? And you can look this up. It's a true story. What they did was they parachuted cats into Borneo to get this, to actually control the rats. And it's absolutely true. They put cats in cages in airplanes, and they went over and they parachuted them to help fix the problem. Good intentions to start with, unwanted consequences due to a lack of systemic thinking. They were dealing with the symptom. They didn't actually understand the problem. They fixed the symptom, and then that resulted in more problems down the road. Systems thinking is the way to help deal with this sort of a situation. And I'll talk a bit more about that as we go. The other area that I'm going to talk about is modeling and simulation, which has been my sort of other passion over time. Modeling and simulation is something, again, we probably don't realize we're doing it, but we're doing it everywhere all the time. And if you look at some of the applications that it's used for, it's everywhere. We'll use it for learning, we use it for training, we use it for playing, we use it for design, we use it for engineering, healthcare, for learning how to fly. It's absolutely everywhere. And even if you don't think you're doing it, you actually are doing it. And I'll explain to you later on why that's the case. So it's all pervasive. It's everywhere, whatever you do. And also, it's actually central to systems thinking. When we actually use systems thinking principles, we actually don't realize it, but we're also doing modeling and we're doing simulation at the same time. Having said that, who recognizes this picture? Anyone seen? Yeah, very good, very good. We got some people, yeah? The Matrix. If you haven't seen this, you have to see this. this movie really makes you think. And the thing it makes you think about is this question. Are we living in a simulation, or what is reality? So I want to think about this as we go, and we'll come back to this one at the end. Yeah. So quickly, a bit about me. I think you all know about this very quickly. So my education, engineering to start with, and computer science in Australia, University of New South Wales. And then in 2014, I finished a master's in systems engineering. And the big gap is that I was applying modeling, simulation, engineering, systems thinking, but I didn't realize what I was doing. And then one day, all of a sudden, these concepts started to make sense. And I started to remember what this was all about. And so I went and did a master's and have been applying. This is my passion now going forward. My career experience, a few companies, but it's always been engineering. And the main one was CAE for the last 24 years prior to this, where I was responsible for technology and for flight simulators in the civil and in the defense space. Great company, great organization. I absolutely loved it. And in terms of other stuff that I do, I think Jagal already mentioned the INCOSI stuff. SESA is the Simulation Engineering Society of Australia, so I'm the current technical director for that. Simulation Australasia is the body that looks after simulation in the Australia Pacific region, and so on the board of that, and really a lot of technical input into conferences and technology and stuff as it goes along. But my passion in life really now is these three things, is to spread the word, to communicate the value, the importance of what is systems thinking, modeling, and simulation, and how they come together to help us understand the world, to deal with complexity, and to make the world a better place. And if anything, as I said, what I want you to go away with is you will remember that this is really what you're doing all the time. So what we're going to talk about today, what I'll cover, I've told you why. I want to go back very quickly to show you an example of how this was applied in not that long ago, in recent times, the First World War. And it actually changed the way the war went, where Germany was winning the war, and then how the UK came back and the Allied forces ended up winning the war. But what they did over there was to apply systems thinking, modeling, and simulation in an integrated, holistic fashion in a very structured way. And hopefully this video will work. But what they were trying to do was they were losing the war, and they wanted to come up with a new weapon. They called it the death ray, and they told their scientists, R&D team, come up with something that we can use to protect ourselves because the Germans are coming all around. This is what happened.
Operational research began in the First World War when science was introduced in order to improve on military operations. In February 1917, German U-boats intensified their assault on Britain's Atlantic supply line, sinking 1 in 10 ships sailing every month. British scientists analysed all available data and created the best possible model to help the convoys survive. They were optimised for size, speed, and timings for sailings. Just 6 months later, losses were down to a remarkable 1 in 200, not only saving lives, but critically contributing to the survival of Great Britain. By 1934, analysts had identified a new problem. Simulations showed that in the event of war, German bombers could easily deliver a knockout blow. By 1938, this knockout blow could be delivered in just 24 hours. The British government asked a group of scientists to explore the feasibility of using radio waves to create a death ray which could shoot down or cook approaching bombers. Instead, scientists demonstrated how radio waves could detect and range aircraft, and radar was born. However, technology alone was not enough. Working in close partnership with RAF officers, the new team was able to combine scientific research with operational experience to create the greatest air defence system in the world. This groundbreaking approach was rapidly integrated to a network of both military and civilian defence assets. With operational research, it enabled the earliest possible detection and interception of enemy aircraft. By the Battle of Britain, radar had increased Fighter Command's defensive capability by a factor of 10, and operational research doubled this to a factor of 20. In 1948, the Operational Research Club was founded, which 5 years later became the Operational Research Society. After the war, the scientists and officers involved in this pioneering approach found jobs in government, manufacturing, banking, health services, business, transport, defence, sport, and well beyond, taking the knowledge and insight of operational research with them, where it has been solving problems and supporting decisions with science ever since.
So operational research was the term they used, but what it meant, or what it was systems thinking, modelling and simulation. Using systems thinking to understand the problem, come up with how to model the system, and use simulation then to predict where things would be and then apply that into the defense context. It was called operational research then. It still is in some places, but what happened was that those competencies and those skill sets broke up into all different industries and they went away and they each became little groups. And we're in the position now where we're starting to see the recognition of the commonality of how this really is all coming together and to bring it back to really what the concept was. So I want to go next into two concepts that were key in my understanding of systems thinking, modeling, and simulation, and primarily in systems thinking and how the world works. And they come back to these two terms, efficiency and effectiveness. And there's a difference between the two. And I've heard lots of debates of what one is and what the other is. I'm going to share with you my personal insight on what that is, and hopefully you'll see the alignment in what Mr. Jagal was talking about actually in some of the slides he saw. So if this thing works, I think I have to be here for this to work. I think so. I'll try and move up. So I want to equate efficiency and effectiveness to the content of the mind. Is what actually happens in our mind and how that translates into these two concepts, efficiency and effectiveness. So we start everything off with, and if you remember the graphic that Mr. Jagal had, data is at the bottom of everything. Data is everywhere. It's pieces of things that by themselves don't mean anything. So you have dates, symbols, names, places. They just are things, but they don't mean anything. We process that data to make it information. We try to look for relationships with the data, and then we collect a name and we put a date to it, and we have a birthday, we have an address of someone. And so we associate data to get information. And so we answer questions of who, where, why, when, and how many. So information takes data and gives us something now that means something to us. We can then go the next step forward. So this answers the question of that. We then take the next step above information and we get knowledge, and knowledge then transforms that process into information to answer the question, how to. So knowledge takes you to, so you know how, knowledge, know-how, right? Those two things go together. So knowledge translates to skills and competencies. Our schools, our universities help us go through this continuum to give us knowledge so that we can learn how to do stuff. We be engineers, scientists, physicists, economists, and we know how to do engineering, how to do maths, how to do economics. And then as we go through this, the knowledge, there is a step change. And something really interesting happens is when we start asking the question, why? And why brings the understanding for the knowledge that we have, and now we really start to apply that. And what happens is as we grow up along this continuum, the value of what we do and the efficiency of doing that gets better. So the more we know how to do something, the better we get at doing it, and the more value we add to the job that we're doing, whether it's we're working in an organization, working at home, whatever it is. When you know how to do something, you do it better. Just as if you don't know how to do something, you have to go and learn it, it's going to take time to do it. And the more we start to understand the why, we grow, and then a real step change happens where we transform the understanding into wisdom. And wisdom is where effectiveness comes in. The difference between the understanding of the knowledge to the understanding the why is the difference between wisdom and knowledge is the same as the difference between efficiency and effectiveness. The key point over here is that efficiency is when we do things right. And efficiency is all about knowing how to do things. Effectiveness is when we do the right thing. And there's a big difference between the two. We can be doing the wrong thing right and we never know that we're doing the wrong thing. But when we're doing the right thing wrong, it's very obvious. True value comes when we start to do the right thing and we do it right. Yeah? So efficiency improves when we know how things are to be done, and it's all about knowledge. We need to have knowledge to be able to do work efficiently. Effectiveness, on the other hand, is we need to know why things are done. Why do we make a decision to go a certain way? And the why things are done is about the breadth of understanding that we develop as we build up our knowledge over time. And some of you probably heard of Peter Drucker, who comes from the management school of things. He sort of puts out a very succinct statement of the difference between what management is and what leadership is. And management is doing things right. It's about getting the job done as efficiently as you can. Leadership is about showing the way, right? This is the way to go, and knowing where to go and provide the direction. And that's the difference really between the two. And the key thing is that systems thinking is that framework that recognizes this. It recognizes that what we're doing through our lives is we are learning. And in that learning, we are building up mental models in our mind of what reality is all about. And as we learn more about information and how to do stuff, our knowledge increases, we build up mental models of things. And as we add experience into that, and we understand why we're doing things, our effectiveness increases. And leadership is when we actually get to the top of this and we start to understand. And we can make decisions because we know why we're going to go somewhere, and we can extrapolate those decisions based on the knowledge we've learned. So these principles are foundational. And systems thinking is the framework that helps us to apply these principles. I'm going to go, so the main part of what I'm going to talk about now builds on all of these things. But it is at a very high level, and if there's time for discussion, we'll go a bit deeper. So I want to talk a bit about systems thinking, and again, I'll just talk about the what and the how. I've told you why I think it's important. So we'll talk a bit about the what and the how, then modeling and simulation, then a bit into systems engineering, and then a bit of discussion. Anyone seen this picture before, this graphic of the iceberg model of thinking? So this is a classic that's used in systems thinking to explain in a quick picture of what systems thinking is all about. So the idea is that anything that happens, we see it first, we perceive it as an event. Something happens and we perceive it through our senses. We see it, we hear it, we read about it, or that sort of stuff. And typically, we try and deal with that, the event. And systems thinking says is that instead of just reacting and dealing with the event, try and think a bit and understand why the event is happening. It keeps coming back to the why question. Ask why something is happening, understand how it's doing it and what it's doing it, not just what's happening and try and correcting it. So systems thinking says is that understand what's happening and then start to look for behaviors or patterns. Once you've understood the behaviors or patterns, try and look for structure or architectures. But most importantly, if you really want to get to the bottom of the problem, understand the mental models that are causing the behaviors. The why is this condition happening? And system thinking says is the deeper you go and the more you ask the why question, and if you get to the mental models, the strongest solution will come from that. The biggest leverage in terms of a solution that will be permanent will come from actually going down and understanding the mental model that was driving the behavior that caused this to happen. By doing systems thinking, when we get involved, when we start to do this, people start to change, not because someone tells them to change, but because they understand themselves why the change is needed. It causes people to start to work together because they realize that it's not his fault or her fault. We're actually all working on this together. And the reason this is happening is because each of us is doing something and I can take my part and fix it, and we all fix our parts and the whole thing gets better. It focuses people on not simple quick fixes, but on a small number of things that are really strong solutions that will actually fix the problem. And in doing so, because of the process, it actually simulates continual learning and really gives us meaningful change. And I think Mr. Jagal talked about that too in some of the work that TUS is doing about the meaningful change that can come out of true application of systems thinking and mental models. We're going to talk about system archetypes. Now, a system archetype is an architecture for a typical problem. And systems thinking gives us a whole number of these models that we can use to look at the problems that are happening in the world. And typically, we'll find that they'll fit into one of these models. And then it gives you a method to work with that to actually find the right solution. I'll talk about two, but there's a whole heap of them, and you'll see the idea. So the first one, and it's called fixes that backfire. It's when we look at the symptom, we fix the symptom, and we really don't fix the root cause, and what happens when that happens. And this was the classic example of Borneo, where the mosquitoes were the problem. They thought that was the problem. They killed the mosquitoes, killed all the other stuff too, and now we had a bigger problem. And there is a graphic that depicts what typically happens in these types of problems. So we have a problem. We fix the symptom. The solution works in the short term because the idea is we need to do something really quickly. We don't have time. We just need to fix it. And the problem goes away. But then there is a delay. And the delay causes another problem. And typically that problem is bigger than the first problem. And they go back again. And the challenge with fixes that backfire is that there is a tendency to apply the same approach again, to fix the symptom and not fix the problem, and the cycle repeats. It becomes a vicious cycle. Now, this is it's not a trivial example, but it's in the scheme of things, we laugh and smile at it. But look at what's happening today in India, in the state of Kashmir. There are riots, thousands of people have died, and it's been going for a very long time. Why did that happen? Now, they're trying to fix it now in terms of the symptoms, but why did it happen? If we actually dig back to the root cause of why that happened, it goes back to the partition of India when the British were there. They partitioned India into India and Pakistan, and they had this state of Kashmir sitting in between. And the challenge was, how do we partition this state? Some wanted to be part of India, some wanted to be part of Pakistan. And they decided that we'll give them something to entice them to be part of India. And they gave them Article 370 in the Indian Constitution, which said that if you were in the state of Kashmir, no one could ever buy land in your state. It will always be yours. And now we are in the situation where clearly that's not a tenable situation. And the country is paying the price for that. A quick fix that comes back later on and causes a much bigger problem than it had in the first place. The second one I quickly want to talk about is shifting the burden. Shifting the burden is where we look at we have a problem. We actually understand what the real solution is, but we're reluctant to apply that real solution, maybe because it costs too much, maybe it takes more time and resources. And so what we do is we apply a quick fix. But we know that there's a better solution, and we apply the quick fix just to get us along, to go past where we're going. And I'll see if I come across this side now. This works. So when we come over here, we apply the fix, the quick fix, and things are okay for a while, but now we have a side effect. And what happens is the side effect actually causes, again, another bigger problem that seems to be a separate problem, but it's actually not. It's actually related to the original problem. And an example of that is food aid. So people are hungry. In Afghanistan, there was a war. People were hungry, starving. And so what do? The first thing is we need to get them food, right? Now, we know that's not the real fix to the solution. There is more to this. Giving them food is not going to help them. But we give them the food, and people are happy now, right, for a while. The real solution is too hard because you have to go and deal with the politics and what's happening in the country. And so that's not done. Now what happens is the food aid continues. Now when the food aid continues, we now have social issues that start to happen around the food aid. You have people that start getting involved in the distribution of that food. Corruption comes in, mafias are formed. And the situation actually becomes worse. So system thinking says, here's the model. If you look at the model, this is what's going to happen if you apply this. Recognize that, and if you're going to fix the problem shortly, also look at the bigger solution, and you can't put it away, because otherwise it'll come back and bite. And so there are a whole heap of other similar system archetypes. Here's one reference, but there are a number of them that actually list 12 of these system archetypes. These are 12 models that apply to almost every problem you see in the world today, and says, if you look at this, here's the pattern, and here's how you deal with it properly. And it provides this archetypical framework. Peter Senge is another person who writes about these. He probably calls them slightly different. The tragedy of the commons is another classic one, where any common resource is overused by people that want it, because each one looks at it from their perspective and gets the benefits, but the cost of that resource is shared amongst everyone else, and the resource deteriorates. So that's on archetypes. I want to now go quickly into how do we understand systems. So when we think of a system, the question is, what is a system, and how do we go about understanding it? And to do this, and this is where the shift happened to me to personally recognize what systems thinking was many years down the track. I actually go back to the aircraft that's on this little logo here, which was this little one over here, which actually is the final year design that I did when I did my aerospace engineering course. That's the aircraft that came out of that in that final year design for me. So I never got to build the aircraft or to fly it, and then now it's come back because it's actually helping me understand the world a bit better. I'll explain how. So when you give a child something, a toy, Lego, whatever it might be, something to play with, have you noticed how they go about understanding or working out what it is? And typically, the first thing they will do to understand it after they played with the bit is they'll try and take it apart, right? They'll try and break it up into bits, and they will see what those bits are. And that's how you understand anything. So designing my aircraft, I had to break it up into its subsystems. So break it up into what's it made up. It's got an airframe, the wings, the structure, control systems, some avionics, flight attitude indicators, airspeed indicators, those sorts of things. Engine and some landing gear. Very basic stuff, but the subsystems that make it up. And then what you do again, you do the same thing again. You break those into their parts and you try and understand how they work, right? And seems simple enough. And then you go about designing these things. So you come up with an airframe, control system, engine, and so on. And then you find that once you put it all together, the engine doesn't have enough power to actually make the aircraft fly. So you have to increase the power on the engine. You increase to get a bigger engine, beef it up a bit, and put it back in the calculations, do the analysis again. And now you find that the engine made the aircraft heavier, so you need more wing span, right? So you increase the wing area. You increase the wing area, that also makes the aircraft heavier. And now you need to go look at the engine, plus you need to look at the control systems, the landing gear, everything. So you find very quickly an aircraft design forces you to do this, is that they are interdependent. No part in the system is independent. The performance of the whole is a function of the performance of each of those individual parts, and every part affects the performance of the whole, and every part affects it in an interdependent fashion. No part is singularly affecting the system. And what you learn very quickly is if you want to optimize a system to do what it needs to do, you don't optimize the parts, you optimize the relationships between the parts. It's about how they connect, not how they are. The only time you fix a part to make it better is if it improves the relationships between the parts to make the whole better. Aircraft or aerospace engineering forces you to do that, but you don't realize that it's systems thinking. But that's what systems thinking is. That's the essence of systems thinking. It's about interdependence. And that tells you how a system works. And if you want to understand how a system works, you follow this methodology. And we have a definition that's focused around how a system works, which Russell Lakoff said. So a system is made up of a whole, made up of interdependent parts, each of which can affect its properties and its behaviors. So that's about understanding how the system is structured and what it does. But that definition doesn't tell you what a system should do. It's about looking inside the system. To understand what a system should do, you have to look outside the system. You have to look at what exists in the environment that it's in. So for example, in an aircraft, you have to look at what's the bigger system that it's a part of. And in this instance, I've just used 3, but there are a whole heap of other systems, right? The airspace management system, how does it interact with everything that's happening over there? The air traffic management system, the controllers that have to be there, what information do they need to know, how do they get that? And how do we keep it flying? The management systems for the vehicle itself. And what we find is that these systems dictate what this system needs to do. So to define exactly what a system does, you don't look inside, you need to look outside. You need to look at the environment that it's in. And we get another definition of a system, which says to understand what a system needs to do, you have to understand the function that system performs within the other systems that it's a part of. Yeah, it's good. And we get 2 methods, therefore, that help us understand a system. The first method is analysis, which we all typically use by default when we say, how do we understand something? We say we analyze it. Analysis is looking in. It's a 3-step process. It takes the system to understand it, break it into its parts, understand what the parts do, put that understanding together in interdependence, and you get what the system does. Synthesis is looking outside the system. It says to understand what a system needs to do, you do the 3 steps in the complete opposite sense. So the first thing you do is you take the system, you understand what are the systems, the bigger systems it's a part of. You understand what those systems do, and then by understanding that, you drive that back down into what the system needs to do. So it tells you what the system needs to do in terms of the functionality. Analysis tells you how the system works. And both of these methods work together to give us an understanding of a system. Now there is, that's a depiction of what I'm trying to say over here graphically. So the interactions inside the system, which gives you the structural or organizational interdependence that happens inside the system, and the operational interdependence of what happens outside, of how the system interacts. And by the way, you can replace this with a technological system, a biological system, or a human being. It's the same thing. Now both of those things work well, and they answer the how and the what question. There's one question they don't answer completely, and that's the why question. And I'll give you an example. You can apply analysis, you can apply synthesis, but those methods will not tell you why the lights on an aircraft are green on one side and red on the other. No matter how much analysis you do, no matter how much synthesis you do, you'll not get that. To understand why, you have to go back in time. You have to look at the history of the system. You have to see where did it come from. And now you understand that the reason those are there is because you go back in the US and it was in the Navy, the boats started it, and why did the boats have it? Because it was on the land, they had it on the land. And why did they have it that way? Because the US had it that way, and in the UK it was the opposite side. And that's why that just stayed. So there are some questions, and particularly the why, that analysis and synthesis will not tell you, but the only way we'll get that is by understanding the heritage, by understanding the background of the system, or the evolutionary interdependence of what has resulted in the system over time to bring it where it is, and also the aspirations of where it wants to go. And so if you look at understanding systems, this is a completely personal view, you won't find this a document in any textbook or anything, is a 3-dimensional approach to understand system. How, which was about organizational independence, which is really looks at analysis, looks inside the system to understand the architecture of how it works, how it fits together, and how it behaves. Synthesis, which looks at what the system needs to do and looks outside the system and its environment and answers the question what the system should do through its operational context. And Genesis, which answers the why question. And it does that through understanding its behaviors and its properties through its historical evolution, both in terms of its structure and in terms of its environment. And we have those 3 definitions which I showed you before. Now the interesting thing over here is that, as I said, it doesn't matter what type of system it is. A technological system, when you buy a computer, if it's got a USB port in it, you know, it's a particular USB type, and if you want to connect a USB to it, you have to get the same or variable type to do that. And how it had evolved over time, you need to go back and look. Human beings, we are our DNA, our structure, our biological makeup, our environment, our families, our work environments, the interactions, the country we're in, our genesis, our historical background, our traditions, our cultural beliefs, religious beliefs, spiritual beliefs. All of those things define who we are. And how we understand systems is using this 3-dimensional approach to do that. I want to quickly jump to modeling and simulation. To do that, another quick story, and then we'll bring it together. So this was a really sad incident that happened back in 2002, where a Russian airline, a Russian Tupolev from Bashkirian Airlines collided with a 757, with the DHL cargo 757 over the town of Oberlingen in Germany. So what happened, and sadly what happened that day or that night was we had an aircraft, a chartered flight coming from Moscow to Barcelona, and it had mostly children with their mothers and going for a summer camp to Barcelona. It was a chartered flight, and this was just a cargo flight, the two air crew and no one else in cargo at the back. Nighttime was very quiet usually at that time. The air traffic controllers in this region, usually there are 2, and they typically take a break because one's enough. And that night, for whatever reason, there was some maintenance work going on. They were fixing things. And the guy was controlling it, and he was still managing okay. And then something else happened. Another aircraft came in for control, and it distracted him a little bit. But still, they should be able to deal with this. And he realized that these aircraft are very close on a collision course, and he needed to do something. And in the rush, he told the Russian aircraft very quickly, he said, you need to descend. He commanded them to descend immediately to a lower flight level. As soon as he said that, within 10 seconds, the traffic collision avoidance system on the aircraft, and all aircraft have that now, which will tell you there's another aircraft coming that you need to do something about, told him there was an aircraft on the collision course, and the traffic collision avoidance system said to go up, to ascend. Now, the air traffic controller told him to go down. The machine was telling him to go up. Almost immediately in the 757, the TCAS, traffic collision avoidance system, told the 757 crew to descend. So the one did the right thing, right? This one said to descend. The other told the other guy to ascend. The crew on the 757 were trained in a particular way, and their training was you follow the aircraft instruments. They didn't think, they just called out descend, and they started descending. The crew on the Tupolev were trained in the Russian tradition, and there actually was a senior captain on the flight deck, and he said, we don't follow the machine, we follow the human being. His mental model was, that's the way you do it. It's authority, you follow people, and you take the orders. And he told them to keep descending. And sure enough, the two aircraft collided, and everyone lost their lives. And the sad story after this, it goes on, is that one of the parents, one of the fathers who lost his whole family, actually tracked down the air traffic controller 2 years later on, ended up going to his house, and he actually killed him on his doorstep. And you see, right, how mental models, right, of what we are thinking, what is going on out there, we make decisions that we believe to be the right decisions. No one wants to do the wrong thing. And we do that through our situational awareness. And there's a model for this, but typically it's this three-step process. We perceive the current situation, we comprehend what it is, and then we essentially make a projection of the future state. We perceive that through our senses. We have mental models of what the world is, what's awareness of what's around us. We factor that in. We then do a simulation in our heads of what's going on, and we make a decision, and we take an action, and it continues. And simulation in that space, so why I was so passionate about it, was that flight simulation is building those mental models so that people don't make the wrong decisions when they're flying in a critical condition in an aircraft. So I'll give you an example of how flight simulation started and how we started to evolve this concept models in flight simulation. So this is an example of a very early aircraft, the Antoinette. What's interesting about these aircraft in those days were the controls. On this aircraft, there were two wheels, one on each side, and one wheel made it go up and down, and the other wheel made it turn right and left. Now you can imagine if you haven't flown this thing before, and the first time you start to learn to fly, there's a very high likelihood that if you're a little bit stressed and you're coming in to try and fly this thing and land it, that there's a very high likelihood you could use the wrong arm. When you want to go up and down, you could use the left one instead of the right one. And that happened. A lot of people died, right? Lots of people died. And so they had to come up with a way of how do we improve this so we don't get people dying because of this. And they came up with the first flight simulator. Pretty amazing innovation. But what were they trying to do? What they were trying to do is to come up with a model that would help them practice this aspect so that it became second nature. So it's like someone comes in front of your car. When you're driving, you put your foot on the brake, you're not even thinking. That's what you want to do, right? You want to keep practicing until you get it right. And so on this side, you have this bar, and the pilot's job was to keep the bar level, while these guys would twist the barrels at the back, and with the two pulleys and the controls, he would be able to practice which arm he uses in which instance to keep the bar level. We had a model of the aircraft that was of relevance to this particular activity. It's not flying, but the point is you had a model that allowed him to train to what he was doing. And this is what models are all about. They are not real. They're an abstraction for a particular purpose. And when we get into simulation, and flight simulation in particular, there's in fact, for training anything, there's typically a progression of how we learn. So we learn with basic knowledge, and then if we've got some technology, we get familiar with some equipment, we use some procedures, operational use, and then some mission training and maybe mission rehearsal. And so what we're trying to do in that context is in the human being, we're trying to get our senses aligned and the mental models created so that if we do this in a training context, we're okay, we can make mistakes, but when we do it for real, we don't want to make mistakes. And so we have to, in simulation, what we're doing is creating models of reality that will trick these senses to make us believe that we are doing that so we can practice it and make it right. And so if you take sound, for example, what makes sound real for us? Our ears hear sound. But there are really, if you think about what makes it real, if you're listening to a band in a concert and then you play it on a stereo and you replay it in a disco or on speakers, you can tell the difference where it's good sound or bad sound. But what that really is there are three things that are making it good or bad for us, and we call that fidelity. And that's where hi-fi came from, right? High fidelity sound was how do we trick this in. And each of our senses has got that. And for sound, it's amplitude, frequency, and vibration. So it's just three fundamental things. And if you get those right, our brain will believe that we're hearing the thing just as it is in reality. And for all of the other senses, there are sets of this detail that has to be added in. And when we look at that, we can make it right. But we have to take reference to the fact of what's important for the particular model that we're trying to create. And if you look at flight simulation, it just looks at these three particular aspects. And I'll show you two simulators. One is for a procedural trainer and one is for mission training. So this is a training system for a procedural trainer. So we're just trying to get someone familiar with how to operate equipment. Not to fly the aircraft, but just how to operate the equipment. Know where it is. Whereas on the other side, we want to teach them exactly everything you need to do to fly the aircraft. So it feels like the real thing. And all of the risky things that you can do, you can try it out. Now, start to think of the models that you would need to create to teach someone to do this versus doing that. And we start to think of different aspects that become important. So we might think of physical fidelity, the replication of pieces of hardware, whether there's a control system over there, over here, and over here there's very little physical fidelity, over there's full physical fidelity. So the model for physical fidelity, very high, detail, very low detail. And we might think of functional fidelity and environmental fidelity, temporal timing fidelity, psychological fidelity, and so on. And the important point over here is to recognize that this is a set of models, that's a set of models, and they're all trying to do a particular thing, but their detail or resolution is different. So the models you might create for the engine, for example, to replicate that, will be different from that. It doesn't have to be, but doesn't need to be the same. This one is very high fidelity in terms of resolution. This one is not. And the recognition of that is simulation forces you to understand that. Models are abstractions of reality that are developed for a particular purpose. And whether we apply them to technology or whether we recognize that's what we're doing when we create models in our brains, that they're all different fidelity, all different resolutions, the concept is exactly the same. So I'll quickly show you two examples of if you have a graph, functional fidelity increasing, physical fidelity increasing that way. And if you draw that up into a matrix, what might be low functional and low physical? Reading books, right? Reading something in a set of notes and simulating in the model in our brain. So it's very low functional, very low physical. If you put that up over here, we might have a computer program like Microsoft Flight Simulator, high functional fidelity, but very low physical. There's no replication of the hardware in the cockpit, right? It's just the simulation on a computer. And if we can build that up in a similar way to have a cockpit of an aircraft, which doesn't work, but it's very high physical, but low functional, to a full flight simulator that sits in the corner over there, which is completely immersive, where you are believing that you're in the real thing because all of your senses are being triggered at the same time, collectively. And so we find that simulation is, a definition for simulation is a model that we then execute over time. A model is a abstraction, and that's the important thing to note, that no model is real. Every model we create is defined for a purpose, and it's limited in terms of what it is. And it might be of a system, an entity, a phenomenon, or a process. The examples of models are those over there. For example, if you want to simulate how to get a surgeon how to work with an ultrasound system, you can create a model of that ultrasound sensor and then teach them on a computer how to do that before they actually do that in real life. We can create a CAD model, a computer-aided design model of a vehicle or a building that we use to then build the building, and we might use models of terrain. And that's the modeling process. It's about abstracting reality for a particular purpose. A simulator or a simulation is essentially a method of taking that model and executing it. Technology provides us with that means. For example, we might take a three-dimensional model of the vehicle over a model of the terrain, and we see that used in a simulator. Now, all of us have played computer games, and exactly that's what's going on. We have models of things interacting, and we're simulating them. Moving on to some examples. Simulation is applied in healthcare, in flight. Flight's the biggest area where this is applied, but the concepts apply across the board. And these models and simulations we're talking about, I'll come to the mind thing in a minute, but they're essentially everywhere. Whether we are doing it actively or not, we're actually applying models and simulation. And this guy made a really important statement, is we always have to recognize that no model is perfect. Every model is wrong, and some of them are useful, including the ones in our heads. Yeah? All right. I'm going to bring it to systems engineering at a high level. Won't go into detail, but at a very quick level, how we put all this together. How many of you actually are systems engineers or apply systems in your work? Anyone here? No? All right, I'll go through this quickly. So why do we do systems engineering? Is because there is a need to deliver something, and typically those are not the things that get delivered. And so it came from a technology perspective. So this is what the customer actually wanted. This is what they thought, and each person thought a different thing, and what actually got delivered didn't even come close to what was asked for. So there's always problems in understanding what's going on. So systems engineering is a framework that helps us deal with complexity and risk. It provides us with a means to deal with what someone is actually thinking and wanting to actually deliver that. Maximizes the chances that we're going to deliver the right solution, builds in the quality, provides a framework, and really provides traceability of the development process. So lots of things. But essentially, from my understanding experience, there's two things that systems engineering does. Just two things. And those two things are, one, it ensures we build the system right. And two, that we build the right system. Now, where did you see that definition before? You remember seeing that at the beginning? Efficiency and effectiveness, right? So what is systems engineering doing? To me, that's what it's doing. It's ensuring we have efficiently doing it and we're effectively doing it. How does it do that? So this is what, I'm going to talk about the what and the how. So sorry, this is what systems take a real world problem and translate it into a solution. Yeah, systems engineering allows us to do that. In COSI, as Mr. Jagal mentioned, has a definition for what systems engineering is, and you can read it over there, but it really talks about process and about how bringing things together. So it says what it is, but it doesn't tell you how to do it, and that's okay, because the how to do it is something that needs to evolve. But one of the things I had the greatest passion for was I think the how to do it is important. And I think the how to do it is the part that's probably missing, and that's where systems thinking or systemic thinking comes in. And so, if this works. So this is a personal view, taking the same language but translating it to how to do it. And the key difference here is that while this is the process, I believe it's the application of systemic principles, and those systemic principles are what I've just talked about. Systems thinking, modeling, and simulation. It's the application of those three principles in that framework that I was talking about in a systematic whole-of-life framework. They talk about a process, an interdisciplinary process. It's a systematic. Process is a systematic thing. And the difference between systemic and systematic is systematic is one step follows the other. Systemic is applying these principles in those steps. That's the difference, right? That's basically the key difference in how you apply that in terms of defining the solution, realizing the solution, delivering the solution, managing it, and then taking it out of service. So, who believes these guys said what these guys said is true? And what they're saying is that everything in the world, no matter what it is created twice at least. Once in someone's brain, and then once you see it in reality. Right? So two creations happen. You have to think about it, come up with a concept, and you have to translate it into something. And then you see the thing. You see this laptop, you see the bottles of water. Someone had that idea, or some people had that, and we translated that into things. And so this is the concept, and systems engineering is the application of that concept. And so these are what these guys are saying. Everything twice, right? Created once in the mind and once in reality. And how does systems engineering now help us do that? And this is what I'm going to show you now. Very quickly, something that took me about 20 years to actually digest, right? So I'll bear with me for a second. So here's a life cycle, a typical life cycle. When we want to do any system, what do we do? First, there has to be a need for it, right? Someone says we have a problem and we need to fix it. We then understand what that need is. We translate that into some sort of requirements. We translate that into design. We develop the design. We deliver the design, test it, and then we utilize it. And then at some point, we dispose of it, right? So it has a typical life cycle. And those two guys that said before said we created twice, yeah? I'm actually going to show you how systems engineering says we actually create it 4 times. And the 4 creations are actually 4 models. There is a need to create models 4 times, and systems engineering helps us do that, which translates in the most efficient and effective way a concept into a solution. So this is a quick rush because this is a 1-hour thing to go through the detail, but I'm just showing you the picture and I'm talking through this very briefly, right? So we start off with the needs. Every need has associated with a set of goals. The goals translate to use cases. And so, for example, if you want a need for transportation, you might have some goals. You want to get there safely, you want to get there in comfort, you want to be able to get there, and a whole heap of other criteria. So you have some goals. Then you might translate that into some use cases for transportation. You might want to go, I don't know, from UB to Beijing, say. So the use case in this case, the goal might be to do that in environmentally friendly way. So you might think of environment requirements. I don't want to have an environment that is too hot, too cold. Pressures should be reasonable. Then there might be a comfort thing, or there might be how long the time takes and so on. And so we end up with a different set of use cases. They translate into specific requirements. We group those into a design, we implement the design, and we build a system. But what's actually happening in that process as we go through this life cycle is that we're actually creating some baselines. We call these essentially the functional, the allocated, and the product. But what those are is more interesting. Don't worry about the technical bit, but really what we're doing is we're taking a conceptual model, which is in someone's mind. We're translating that into a logical or a functional model of the system. And really the idea is to make this as close as possible to this. We're translating that functional model into a physical model, and then we're implementing that physical model. And so inherently, it's all about modeling. It's about understanding the concept over here and translating that into a functional baseline. And we end up with a conceptual model of the system of interest. We then map that in the engineering process into a physical architecture, and we end up with a physical model of the system, and then we build a physical model. And you've seen that in blueprints of buildings and so on. What systems engineering is about then is, in the first step, is extracting the model that's in someone's head and sharing that model with them by putting it into your own head as a systems engineer, and then sharing that with them so you can correct that model and you agree that this is the model that we're trying to build from a conceptual perspective. And then you translate that through mapping into a physical architecture, and you do the same thing in terms of developing a physical model and then translating that into the actual implemented capability, and then keeping that up to date into what's going on. And the job of systems engineering or systems thinking in that regard is this middle bit that helps us take that concept and to deliver a need. And in the process, we are creating models of the system. A functional or logical model, which we translated as one that we both understand, and then we translate that through the engineering process, of this is where the technical bits come in, into the capability itself. So inherently, it's about models. And we develop simulations of those models, depending how sophisticated we get, where we can change things and see what happens as things go on. So to bring it all together, just a quick recap. So recall efficiency and effectiveness, the difference between the two. Efficiency is about knowing how to do stuff. Effectiveness is doing why things are done. And we get the basic difference between them over there, and the fact that leadership and management are exactly the same sort of thing. Systems thinking is a framework that helps us understand that and apply that to make the world a better place, really. What modeling and simulation is, the definition of a model, which is really an abstraction of reality for a particular purpose, and a simulation is then executing that model over time to do something. A methodology for understanding systems, a three-dimensional approach. If you want to understand how a system works, you look into the system, and we have a definition of what that is over there, and it's all about the interactions and the interdependence within the system in terms of its structure. Synthesis looks outside the system and what the system does, and it's about operational interdependence of the interactions the system has with the environment that it's in and other systems that exist. The why question, the heritage of the system, which explains how it behaves, which looks back at the evolving structure and the evolving environment of the system, and the three definitions that go along with that to tell you what a system is, and how systems engineering helps translate uses those systemic concepts to build models of the system, starting off from someone's head, what's in someone's mind, into a functional model, translating that into a physical, and then building the real system behind it. Now here's the interesting bit. So I've talked a lot about the technology, and this is what my life was for a long time, was about technology. But really, if you think about it, and as Mr. Jagal had to start with, just examine for a second what's actually happening in our brains. And you start to see the parallel, hopefully. Our left brain is doing the analysis. Naturally, our left brain is the analytical brain. It's breaking things down into its parts. It's trying to understand how the parts fit, and it's trying to understand how things work. If you're more an engineer type person, you pretty much think most of that time you're trying to work out how things work, yeah? And this is what your brain is doing. Our right brain, in the meantime, is doing the complete opposite. It's looking for relationships. It's trying to understand, how does this fit into the world? What are the interactions? What are the relationships that exist behind this? And our backgrounds, our cultural beliefs, the paradigms that we grew up with, what our parents taught us, what our cultures taught us, is focusing our understanding, and has developed these models within us that we don't even know that are there, that are guiding all of this stuff. And all of the time, every single second of the day, these models are working, and we're simulating reality. And we're thinking about what's going on, and we're making decisions. Every decision that we make, it is a decision based on what our senses are perceiving, what the models in our brains are telling us, what we understand them to be based on our heritage, and we're making decisions in that space. These two guys talk a lot more about this, Peter Senge and Umberto Maturana, and the recognition that this is what's going on was enlightening, to say the least. Umberto Maturana talks about the Santiago theory of cognition, which really talks about how the living thing evolves, and we create our reality through what's happening in our brains. And Peter Senge talks more about mental models, of how they are so deeply ingrained that we don't even know that we're applying them. It's like if I asked you to explain how you walk. It's really hard to do that, because it's so ingrained in you. It's like when you first learn to drive, especially if you had manual cars, and which don't exist anymore, but when you had to learn to change gears, with the clutch, when you first had to do that, it was really hard, and then it became second nature, and you didn't think about it anymore. It goes into your subconscious. And that's what mental models are. They build up over time, and they're behind us in our subconscious. We don't realize we're doing it. And he went on to create the term autopoiesis, which is self-creating. And he said the human being is the only organism that we know that actually self-creates its reality through the way the brain works, through the way we create our mental models. And this statement of his sort of sums that up. So when we actually look at the world and we see it today, every one of us is seeing the world differently, because we don't perceive the world we see just with the light that goes through our eyes. There's a whole heap of stuff that happens after that. The light goes in the brain, it gets processed through our mental models, it simulates what's going on, we make decisions, and so everyone's reality is different. Every single one of us has a different world in our brains of what it is out there. And where there is a bit of correlation, we call it normal. Where the correlation doesn't happen, then we call them abnormal. And we look outside the curve and say, those people are crazy, right? Or I can't get along with that person because he just doesn't think like I think. It's because we have different mental models. Yeah? We have different mental models of what reality is. And this statement sort of goes on from that, is that when one human being tells another human being what is real, what we're actually saying is, I have the truth, you don't, right? My reality is better than yours. Can that be the case, right? It all comes back to this stuff. The reason why someone behaves the way they do is not because they're doing it because it's wrong. It's because something happened over time that caused their mental models to come to the point at which they are today, where they're making those decisions. And those mental models, they're so deeply ingrained, we don't even know we're doing it. So how do we change our mental models? Two things. I personally believe there's probably other ways. One is to learn things that you're not taught, to go out there and do something different, right? Learn something different, and that makes you think. And when you start to think, the other way to do it is to reflect, is not to react. And when we start to think, we actually tend to change our mental models. And systems thinking is the recognition of this, and most importantly, the reactiveness. When we react, we're dealing with a symptom, but we need to take time to actually get to the root cause, to the mental model that's driving the symptom, and then make a decision which will give you the right solution or the best solution in that space. This graphic actually sums it up so well. What's the difference between what is true and what is the truth? How many wars have we had because people say what I believe is true, and if you believe something different, and we're going to fight about it? And can you not see that we can have two things that are true from a single truth that are both completely different? And if you look at the models around us that we use in the world every day and we think to be real, the laws of physics, mathematics, they're all models. You take Einstein's theory of relativity, E is equal to mc squared, right? It defines physics on a large scale. It defines how planets interact. But it doesn't define how molecules and atoms and electrons interact. We need another theory for that. We have quantum mechanics. So we have two theories, right? We have a theory of relativity and quantum mechanics. Now, isn't that interesting? We have two theories that define reality, or two perspectives. Now, we know that they're defining the same thing, just from different perspectives. There's no fight there. But exactly the same thing, right? It's a truism. And I think one of the lessons I've learned is whenever you see that, whenever you think that you know the truth, if you take it to the extremes and you start to get to a point where you imagine this, as you go to the extreme and get to the corner, what will happen to this shape? It will change, right? It won't be a square anymore, and this won't be a circle anymore. And that's what happens with relativity and with quantum mechanics. If you take relativity as you bring it down into the molecular scale, it stops working, it does strange things. Quantum mechanics works fine at the electronic scale, at the micro, but as you bring it up, it doesn't work anymore. And I think that tells us, when we see those things, it tells us that maybe we don't have a good picture of what the real truth is. It's just a perspective. It's a model. The model is an abstraction. It's not the real thing. And when we do that, we recognize that, and now we can start to probably have compassion that maybe someone else has a different perspective on things, and maybe we make the world a bit of a better place by not fighting so much. Yeah. Last slide after this. So, some of the differences to sort of take away, if anything, efficiency and effectiveness. The two things to me that changed the way I thought were the recognition of the difference between the two. One is about doing things right, the other is about doing the right thing. Knowledge and wisdom is the same as the difference between efficiency and effectiveness, as is management and leadership. I didn't go into detail on this because of time, but it's a systems engineering concept. The difference between verification and validation is exactly the same. Verification is to do with efficiency and knowledge. Validation is used to do with wisdom and effectiveness. And systematic versus systemic. Systematic is about following steps. Systemic is about applying systems principles. And to finish off, you remember that first slide? So the question it had is, are we in a simulation? Time's gone a fair bit. I'll tell you what, I actually think that's probably not the question to ask, because I don't know whether we'll ever get the answer to that. But I think the question that's probably more relevant in this context is, where is the simulation happening? Yeah? And I think I'll finish off over there. So, thank you. That's my time.